For millennia, humanity has gazed upon the mesmerizing expanse of stars, yearning to explore the countless worlds hidden with them. With trillions of potential neighbors out there, the vast distances separating us remain a frustrating barrier. While our robotic emissaries have ventured across our solar system, interstellar travel remains a daunting feat. To bridge the interstellar gulf and reach for distant suns, we need a revolutionary propulsion system. This engine wouldn't just need immense power to escape the sun's grasp, but also incredible resilience to endure the immense voyage. Until recently, such technology belonged to the realm of science fiction. However, exciting scientific breakthroughs are pushing the boundaries of what's possible. Let's delve into what a future hyperdrive might look like. The vast chasm of space, a challenge for modern engines. The universe is a place of staggering distances. Even our most advanced engines struggle. A trip to the moon takes weeks, and Mars can take over 6 months, even with the most efficient path. Our legendary Voyager probes, traveling for 45 years, have barely left our solar system's doorstep. They'll spend millennia drifting through the outer fringes before reaching the Oort cloud. The fastest spacecraft, the Parker Solar Probe, will reach a record-breaking 194 kilometers per second in 2025. But the speed relies on the sun's gravity, trapping the probe in our star's clutches. It will eventually succumb to the sun's immense heat. Chemical rockets, the workhorses of space travel, seem to have reached their limit. They simply aren't powerful enough for interstellar journeys. While alternative concepts like nuclear pulse propulsion or solar sails exist, significant challenges hinder their development. However, overcoming these hurdles is a necessary step for future space exploration. Another critical challenge for long-distance travel is reliable and powerful energy. Current spacecraft are small and rely on dependable but weak power sources. Research probes often use isotope batteries, which weaken over time. The Voyagers, for example, have had most systems shut down for years, coasting on inertia. Space stations like the ISS combine solar panels and radioisotope generators, but most of their power goes to life support. Ion engines are just for minor orbital adjustments. A spacecraft for a long-duration mission, whether to a distant planet or star, would need significantly more power. The vast majority of a journey to another star would be through empty interstellar space, devoid of readily available energy sources. Even the light from distant stars weakens significantly, dissipated across the immense emptiness. Fueling the voyage, the search for an ultimate power source. Interstellar travel demands an independent, powerful, and ideally limitless source of energy. To find a solution, we need to delve into the cosmos itself. The universe is a treasure trove of remarkable physical processes, some of which may hold the key to harnessing stellar power. Let's take a brief detour to explore a fascinating discovery. In 2017, a team of scientists from Princeton and Hong Kong unveiled a mind-boggling device that seems to defy physics. This microscopic creation, consisting of 2 tiny toothed silicon plates spaced a mere 100 nanometers apart, could generate a small amount of energy, seemingly from thin air. This phenomenon appears to contradict the fundamental law of energy conservation. The traditional view of the universe suggests a simple composition of matter and energy. However, the reality is far more intriguing. Harnessing the vacuum's energy, the Casimir effect. The seemingly impossible energy-generating device is built on a principle called the Casimir effect, discovered in the mid-20th century. Here's the basic idea. Imagine 2 close-set metal plates in a vacuum. They experience a tiny attracting force. This phenomenon is linked to Heisenberg's uncertainty principle, which allows for zero-point vacuum fluctuations. These fluctuations are pairs of virtual particles that constantly pop into and out of existence everywhere in the universe. They have incredibly short lifespans, lasting only 10 to -24 seconds before vanishing. In open space, any type of virtual particle can appear. However, between the closed plates, only particles with specific wavelengths can exist. As a result, the pressure from external virtual particles pushing on the plates is greater than the pressure from those inside. Imagine a slight vacuum within the space between the plates, as if a bit more nothingness was squeezed in. This minute pressure difference can be converted into a tiny electric current, which is what the Princeton and Hong Kong researchers achieved. While the current was weak, the principle is groundbreaking. It hints at the possibility of extracting energy from seemingly empty space. Even a low-power, inexhaustible source would be revolutionary. Imagine the Voyagers equipped with such a battery, still sending data back to Earth. It opens doors to deep space exploration. The Casimir effect has intriguing consequences. One is the Scharnhorst effect, which predicts that light speed between the plates might exceed the usual 300 km per second due to the absence of collisions with virtual particles. While technically impossible to test yet, the theory suggests fascinating possibilities. Warping space-time, the Alcubierre drive. Consider the Alcubierre drive, a theoretical engine that could propel a spacecraft faster than light. Scientists Gerald Cliver and Richard Abusey from Baylor University explored its potential feasibility. They merged the complex equations of quantum field theory with Einstein's general relativity, providing a more robust foundation for this audacious concept. Quantum field theory suggests that space isn't limited to just 3 dimensions, but has many more. However, these additional dimensions only become apparent at the microscopic level. Cleaver and Abusey used this theory to analyze the Casimir effect. Their calculations suggest that manipulating the properties of light and its speed might be achievable through powerful energy manipulation. This connection between the Casimir effect and the Alcubierre drive is intriguing. It hints at the possibility of using exotic forms of energy to warp spacetime itself, potentially achieving faster than light travel. Warp drive via the Casimir effect, a glimpse into faster than light travel. The Casimir effect offers a fascinating twist on the Alcubierre drive concept. Imagine manipulating space around a spaceship, compressing it behind and expanding it in front. This could create a region similar to Alcubierre's warp bubble, enabling faster than light travel. Crucially, this wouldn't violate relativity. The ship itself wouldn't be moving faster than light. The warped space around it would propel it forward. However, the biggest hurdle remains the immense energy requirement. Some estimates suggest converting an entire planet's mass into energy to create a usable warp bubble. Here's where the Casimir effect comes in. If researchers can scale Casimir-based generators to the necessary levels, we might be able to tap into a virtually limitless energy source anywhere in the universe. Of course, challenges beyond propulsion remain. Space is a harsh environment. Deadly radiation bombards everything, damaging cells and potentially causing mutations in future generations. Thick metal shields or specially tuned magnetic fields offer some protections, but both approaches have trade-offs. Another threat lurks in the form of micrometeoroids and cosmic dust. At such high velocities, even a tiny particle can pack a devastating punch, potentially breaching a spaceship's hull. The long road ahead. Challenges beyond propulsion. Even with a revolutionary engine, interstellar journeys pose immense challenges. Repairs in the vast expanse of space are practically impossible, making a single hull breach potentially catastrophic. Moreover, a self-sustaining ecosystem becomes essential for a long-term mission without resupply from Earth. International research teams are tackling this problem. The ISS has successfully grown plants for both scientific study and consumption, demonstrating the potential for onboard farming. Engineers are creating systems to recycle waste, including human byproducts. However, a fully functional, closed-loop ecosystem within a spaceship remains a distant goal. The unknown also looms large. Our spacefaring experience is limited. The universe holds countless mysteries. The long-term effects of exotic environments encountered during interstellar travel in the human body are largely unexplored. Undoubtedly, future explorers will face unforeseen challenges, each solved problem leading to new discoveries and a deeper understanding of the cosmos. Perhaps one such discovery will fundamentally change our perspective on the universe, revealing wonders we can only dream of today. And if you like this video, click the next one shown on the screen. I'm sure you'll like it. Thanks for watching.